This is chapter 23 for AP Chem Review on nuclear chemistry, a topic we covered more in Chem 1 than we did in Chem 2. The first thing it talks about is radioactivity, an unstable nuclei emitting particles or radiation spontaneously. The transmutations refer to the results from the bombardment of a nuclei by particles. Next slide we talk about balancing nuclear equations, something we did a lot of in Chem 1. First off, we need to go over the particles and their symbols. So we have protons, neutrons, electrons, positrons, and alpha particles. So if you look over here on the board, again, a proton is typically going to be shown as a 1, 1, and a p because it has a mass of 1, atomic number of 1, and again the p for proton. You might also see it as a 1, 1, and an H otherwise because a hydrogen nucleus is just a proton. A neutron, on the other hand, has a mass of 1 but no proton, so atomic number is 0. So this would be the symbol for a neutron. The next one was electron. Electron is often given as a 0 for a mass and a -1, so there is relatively no mass for an electron. We give it a -1 atomic number. You might also see it written like a beta particle, which is like this. So again, either the beta particle or electron meaning the same thing in this case. A positron, very similar to this, it's going to be a 0, a +1, and an E. So that would be your positron symbol. I've seen literature say it could be shown as a 0, +1, and a B for beta as well. I'm not really familiar with seeing it that way, but it could be, I suppose. The last one is the alpha particle. Alpha could either be the A for alpha. It has a mass of 2 because it has 2 protons and then 2 neutrons to get the mass of 4. Or you could see it as 42He because He is a helium nucleus, so it could be that as well. So those are all symbols that we went over in Chem 1 when we studied it, and when doing that, we were then able to show alpha decay, beta decay, positron emission, electron capture. So I'm going to give you an example of each of those right now as well. And the first one I'm going to do is polonium-212 going through alpha decay. So if I say polonium-212, that means the mass of polonium is 212. If you look on your periodic table, it has an atomic number of 84. Now when things go through decay, what means is you have an unstable element, and now it's going to change. The arrow represents the change that's occurring. And if we're showing the alpha decay for this one, I would first then draw the alpha particle, 42He. Now I have to figure out what is the new element it becomes. If the mass was 212 here, conservation of masses, 4 plus something equals 212, which in this case would be 208. 2 plus something equals 84, that must be 82. Look on your periodic table, what is element 82? That's lead, Pb. So this would be the alpha decay for polonium-212. Let's say beta decay for cesium-137 is our next one. Here's cesium-137. Cesium's atomic number is 55. If it goes through beta decay, 0, -1e or 0, -1b, plus, and you have to figure out the particle. Mass does not change with beta decay. Alpha decay is the only one that really changes the mass. Remember, an alpha particle is 2 protons and 2 neutrons to get it a mass of 4. Mass does not change for beta decay. -1 plus something equals 55. That something must be 56. Kind of unusual that you move up an atomic number, but what's happening is it's adjusting the proton to neutron ratio, and in this case, barium, Ba, would be my element. So this would be the beta decay. Positron, a good example there would be potassium-38. So I'll rewrite this one up above here. Potassium-38, look on the periodic table, what's the element number or atomic number of potassium? It's 19. Positron emission, 0 plus 1e, plus, what does it equal? 38. That must be 18, which is going to be argon. So again, here's your positron particle. Here's the argon that it made, often referred to as the daughter product, because the parent is unstable. And the last one is electron capture. You'll notice with all these I've done so far, we've always had 2 things on the right side of the arrow. The unstable element becomes the particle and the new daughter product. Electron capture is the one time you will have 2 things on the left side of the arrow. So if we do argon-37 as an example, Electron capture means it's going to capture an electron. So electrons in the inner orbit, the nucleus is going to absorb in. And what this is going to make then is a mass of 37. 18 plus a negative 1 is going to be 17. And that will be chlorine there. So again, these are the 4 types of decay equations that you should be familiar with as you're working on this. The next slide, what we're going to go over is what's referred to as the band of stability. So there's several reasons why we could go through these decays in the first place. The first is the neutron to proton ratio. So you often will see this table here that shows what's referred to as the band of stability. The band of stability is showing where the atoms are going to be most stable with their isotopes. Remember, an isotope is the same element with a different number of neutrons giving it a different mass. And early on, small elements want a 1-to-1 ratio. That's what this line shows right here, of protons to neutrons. As you get larger, they want to get closer to the 1.5-to-1 ratio of neutron to proton. So you need more neutrons when you get bigger. We talked about in Chem 1 the reason why is that there's a strong nuclear force holding the nucleus together while there's repulsion between protons trying to rip it apart. And repulsion acts over large distances, so the bigger you get, the greater your Z or your atomic number is, or number of protons, the greater you get, the more neutrons that you need to try to hold that nucleus together. So that's what that graph is referring to, and that's what I mean by neutron-proton ratio. You want it to be 1-to-1 for small things, more like a 1.5-to-1 neutron to proton ratio as you get larger. For some reason, even number protons and neutrons are more stable than odd numbers. I haven't found a reason why. It's just stated in a lot of literature that when we look at stability of isotopes, those with an even number of protons and neutrons are more stable. Lastly, elements higher than 83, so really even 82, lead is usually the cutoff point, 83 and higher often referred to as unstable. These elements are going to be unstable. The reason why they're unstable is because they have too many protons. You're so massive, there's so much repulsion going on that you are going to go through decay. So when we showed you all those decay equations a little while ago, the reason for alpha decay, beta decay, whatever it may be, is to become more stable. And these are the reasons that you would be unstable to begin with, and those decays are trying to counteract. Binding energy is referring to the energy required to break up a nucleus into its component protons and neutrons. So there's an energy that's associated with how much energy is required to hold the nucleus together, or if we ripped it all apart. A nucleon is a term that we didn't use a lot in Chem 1, but it's just referring to protons and neutrons, so things within the nucleus. E equals mc squared is an important equation. Again, this is the Einstein equation that most people are aware of, but how it relates to nuclear chemistry is something referred to as the mass defect. The difference between the mass of an atom and the sum of the masses of its protons, neutrons, and electrons. So in other words, an atom actually has a smaller mass than all of its parts combined. Now this is contrary to the conservation of mass law, but conservation of mass law does not really address how energy and mass are related. Again, the C we talked about in earlier units is the speed of light. And again, this equals mc squared is showing that when you add up the protons, the neutrons, and the electrons, the mass of those combined is slightly larger than the mass of an atom when it's all put together. Because a little bit of that mass is converted into energy that holds it together. That's the binding energy that we refer to. And mass defect is referring to the fact that we lose a little bit of mass in the formation of an atom. The next thing to go over is natural radioactivity. There's a decay series, so most things don't just go through one alpha decay and are done. Instead, things go through a lot of different types of decay to get to where they need to. So if you recall from Chem 1, we would do series of steps of decays in order to get that there. A half-life equation, I'm going to give you an example of. So let's say carbon dating has a half-life of 5,715 years. If we started with 5.0 grams of carbon-14, how much time must pass when there's only 0.625 grams remaining? So if we look up on the board here, how I'd solve that, first off, one of the things that it doesn't mention within the problem, but carbon-14, again, the reason why it's unstable is it has 6 protons and 8 neutrons to get the mass of 14. It would want a 1-to-1 ratio. Not that it's mentioned within this problem, but carbon-14 typically goes through beta decay to form nitrogen-14, which is now a 1-to-1 ratio. It's a lot more stable. Now, what you would start off with is the 5 grams of carbon-14. What we're going to do is we're going to divide by 2 and divide by 2 and divide by 2 until we get to 0.625. After one half-life, half of the carbon-14 has decayed into nitrogen-14, the other half is still carbon-14. So that's where one half-life is passed. After a second half-life, I'm now down to 1.25 grams. If I go through a third half-life, I should end up with the 0.625 grams. Hopefully my math is correct there. So what I would do then is count that we have 1, 2, 3 half-lives. If I now take my 3 half-lives and multiply it by the years for one half-life, that will get my final answer of how much time must pass for 5 grams of carbon-14 to decay into 0.625 grams of carbon-14, which I get 17,145 years. We didn't really go over a lot of nuclear chemistry in Chem 2 because we covered it in Chem 1, and as you're hopefully seeing, it is some pretty basic things, so this is about as complicated as the math gets for this, so that shouldn't be too tricky. If we move on, we talk about synthesized elements in this unit as well. Synthesized units are the man-made elements. So these elements, again, happen with a particle accelerator. Typically what happens is they take uranium, that's called a transuranium element, because they take uranium and they bombard the nucleus with more particles. And if you can add a couple protons to it, now you've increased the size of the atom. These are all the outlined elements on the bottom of your periodic table. They're very unstable. Because they're larger than element 83, they are going to go through decay right away. But synthesized elements is one type of element that we have to be aware of within nuclear chemistry because we make them by nuclear means of the particle accelerator. Fission is another thing we have to address. Fission is when a heavy nucleus divides into smaller nuclei and energy is released. Now we often talk about fission being the splitting of an atom. Technically, you are not just cutting an atom in half. This diagram actually does a pretty good job of showing here's a large nucleus. And what will happen is we'll add either a neutron or a proton to it. And that addition makes it so unstable that it's not just going to go through an alpha decay or a beta decay. Instead, what's going to happen is it's going to break into 2 smaller atoms. Now this particular picture is also showing what's referred to as a chain reaction, where when the big atom is broken up into 2 smaller ones, more neutrons are left behind, which will add to another, let's call it uranium isotope, which will split that into more, or this one. You get this chain reaction or domino effect which occurs. But again, things to keep in mind is 1, splitting an atom doesn't mean you're cutting an atom in half. You're adding a neutron and making it so unstable it breaks into half. And then the chain reaction shown there of not only do you have elements as a byproduct, but you also have neutrons which then can hit the next uranium atom. Critical mass, again, is referring to that mass at which it's going to be at the point where it could go through that chain reaction. Atomic bombs that we dropped in Japan are fission bomb examples. Nuclear reactors are also good examples of that. So power plants use fission energy. Fusion, on the other hand, is combining small nuclei into large ones. Thermonuclear reactions, which occur at high temperatures, would be falling under this category. Fusion reactors have plasma energy within them. Plasma is something we don't talk a lot about in Chem or Chem 2, often referred to as the 4th state of matter. It's when you have a gas with a lot of energy in it. Hydrogen bombs are a good example of a fusion, where you have 2 hydrogen nuclei, usually hydrogen with a mass of 2 and hydrogen with a mass of 3, and they come together. And when they come together and they fuse it to make a helium, a lot of energy is released in that fact. Just like in fission, when you split an atom, a lot of energy is released as well, because the energy that was holding that nucleus together is now released. The sun is another great example how fusion works, because that is how we get our energy, is from hydrogens fusing together. Most of us showed a video in Chem 1 of how if hydrogens ran out in the sun, heliums would start to fuse together, and carbons and so on and so forth, until we get about to iron. And then we can't fuse together anymore because there's too much energy required to fuse that big of an atom together. But fusion is taking small nuclei usually and bringing them together. The last couple of slides bring up more of how could we use this. Radioactive isotopes is one of the things that it mentions. Radioactive isotopes are often used in medicine as a tracer. So atoms of an element are used to trace the path of a chemical or biological process. So if it's a dye that you drink or if it's a pill that you take, they have an isotope that they know is going to go through decay. And then they can give you maybe a PET scan, which positron emission is the PE part of PET scan. So maybe they can track where it's going to be going throughout your body to see where their problem is. And again, I mentioned that's used in diagnostic medicine. The last thing is biological effects of radiation. Penetrating power is something that we have to mention. Alpha particles commonly are bigger molecules or bigger particles, so those can only penetrate through, say, air. A piece of paper is usually enough to stop an alpha particle. So they're big, they're slow moving. Beta particles, on the other hand, are smaller. Think of an electron. They can pass through paper pretty easily, but aluminum foil is usually enough to stop a beta particle. Gamma is that energy associated with any type of decay. So when things decay and they break apart, what's going to happen is they're going to go from a high energy particle of gamma, can go through paper or go through aluminum foil. Usually you need a thick sheet of lead or several yards of concrete in a nuclear reactor's case in order to penetrate through all that. The last thing to note here is that radiation will remove electrons, causing ions and free radicals to occur. So when those gamma particles are absorbed by whatever may be there, they can form ions in your body or free radicals. And in Chem 2, when we talked about Lewis dot, we talked about free radicals are those extra electrons that are unbonded that can react with things and cause a lot of problems within your DNA synthesis. This is the end of our nuclear chemistry chapter, which is, again, chapter number